Hi everybody, and today we're going to be talking about RC circuits. And the most basic RC circuit is one in which you have a capacitor in series with a resistor. And we're going to start with the case of a charged capacitor and what happens when we put a resistor in series with that charged capacitor. So how do we get the capacitor charged? Well, consider the case where you have a capacitor and a battery, and if the capacitor is initially uncharged, when we flip the switch, the capacitor will immediately charge, and I'll be left with a positive plate and a negative plate. And the total amount of charge on the capacitor, if it has a capacitance of C, then the total amount of charge will be equal to Q. Okay, from Q is equal to CV. And now, if I open up that switch, what happens when I remove the battery and replace it with a resistor? Okay, so what's going to happen? Well, if I consider the voltage across the battery, I'm going to label that as V naught. Okay, it's previously what the voltage of the battery was, but if I look at the voltage across the capacitor and label it as V naught, this is what the initial voltage across the capacitor will be. And it will be charged with an initial amount of charge Q naught, and Q naught and V naught will have this relationship. Now, qualitatively, what's going to happen when I close the switch? Okay, when you close the switch, qualitatively, current will start to flow. Will then have a complete path for the negative charges that are able to move off of the negative plate, and they will move through the resistor onto the positive plate. When the switch is flipped and there's a complete path through the wires and the resistor from this plate to this plate, there's already an electric field here, right? There's already an electric field here. And what's going to happen is there's going to be a completed electric field inside the circuit, and it's that electric field which will then set up a potential across the resistor, and current will then flow through the wires as a result of that established electric field. And when that happens, again, my current's going to start flowing. The current through the resistor is representative of the current through the circuit, okay? The current at all points through the circuit must have the same value, okay? Since this is a single loop, it doesn't matter if I put my ammeter here, here, right by the switch, right by the resistor on either side, here, here, here. No matter where I put my ammeter, the measurement's going to be the same, okay? Now, the current will not stay the same through time. If my resistor were not here, and I just had a conducting wire, and I closed the switch, then the plates would discharge nearly immediately, okay? But because there's a resistor here, that resistor resists the motion of that charge. Some current will initially be established, but then that resistor is going to act on that current, and it's actually going to impede the flow of that current. And as a result, the process will not be instantaneous. Okay, we don't know what it's going to look like yet, but we know it won't be instantaneous. But what that tells us is, over time, the amount of charge on the plates, Q naught, will diminish. Over time, because the charge on the plates will diminish, the voltage across the plate is going to diminish. That means the voltage across the resistor is going to diminish. And by Ohm's law, if the voltage across the resistor diminishes, then the current will diminish. So qualitatively, we expect all of our quantities to decrease in this case. So how do we show this? What do we do? Well, when I close the switch, now I'm going to draw the direction of the flow of the electrons. Conventionally, we define current as the flow of positive charge, and so positive charge would flow this way. But I'll draw the flow of the negative charge. So my negative charges are going to flow this way, right? And the electric field is going to establish a current through the entire circuit, okay? So as soon as that electric field is established inside the wires, whatever free electrons are right next to the positive capacitor plate are going to be drawn to it, and every single point in the wire will have electrons flowing through it in the same direction, okay? And remember that the definition of current is equal to the derivative of the charge with respect to time, okay? So keep this in mind. So what we're going to do is we're going to derive a differential equation that describes how the charge on the capacitor plates change, and from that we will infer all of the other quantities, okay? So here's how we're going to do it. Remember that the voltage across both of my components has to be simultaneously the same in magnitude, because whatever voltage appears here has to appear here, since this is a single loop. So if I were to think of my capacitor instead as a battery with potential V naught, all of that potential would appear across my resistor. But this is qualitatively no different. I have a source of voltage, even if that voltage is variable, and therefore the only component that it's hooked to must feel that voltage. So the voltage across the capacitor must equal the instantaneous voltage across the resistor in magnitude. Their absolute values must be the same. But remember, if I consider this as a source of voltage, then my resistor is using up that voltage. Or if this is an energy source, then my resistor is using that energy. And so what we have is, and I really should say that this is the voltage of the capacitor. It will change with time. And the voltage of the resistor must add up to 0, right? And that's from Kirchhoff's rules. The voltage drop or the voltage change across a given loop must be 0. And what that leads us to is that the voltage across the capacitor is equal to the negative of the voltage across the resistor. Okay? Actually, I won't erase that just yet. So the voltage across the capacitor is equal to the negative of the voltage across the resistor. But from the definition of capacitance, right, remember that C is equal to Q over V. These are the initial quantities. That's a specific situation. And therefore, V is equal to Q over C. So this is going to be Q over C. But V is equal to IR through the resistor from Ohm's law. So this is going to be IR with a negative sign. But I is equal to the derivative of the charge with respect to time. So I can insert dq dt here. Okay? So here is, this should be C. So I have Q over C is equal to dq over T times R. And I want to solve this equation for Q as a function of time, okay? So we're going to solve Q as a function of time. And let's do this up here. So I have Q over C is equal to negative dq dt times R. So this is a differential equation. And what we're going to do is we're going to solve this equation using initial values. Okay, so you can make this into a definite integral, but we're going to solve it as an indefinite integral and use initial conditions. Okay, but because this is a differential equation, what we're going to do is not what a mathematician would tell you to do. We're going to solve it a slightly less nuanced way and a little bit more brute force. Mathematicians would often tell you if you have a differential equation of this type, then you would need to use something like an integrating factor to do it completely appropriately. What we're going to do is we're going to treat our differentials as algebraic quantities, and in many cases you can get away with this, especially in physical cases. So with that in mind, what we're going to do is we're going to say, I'm going to multiply dt up on this side, and I'm going to divide by r, and I'm going to divide by q to get my q's together, and the result of all of that is this. Okay? So if I divide by r, I get RC on the bottom here. Divide through by the negative sign, multiply by dt, and divide by q. So I get dq over q is equal to negative dt over RC. Okay? So this is our equation that we can now integrate. I have differentials on both sides, and the differentials are in the numerator. Okay, so I'm going to integrate both of these sides, and that's a wonky looking integral symbol. That's still a little wonky looking. It's a little bit better. So this side just turns into the natural log, right? So this is just natural log of q. This side, I can take 1 over RC out of the integral because R is just a constant, it's the value of the resistance. C is just a constant, it's just the value of the capacitance. And so I'm left with the integral of dt. So this is going to be just negative 1 over RC times t plus my integration constant. And I'm going to use k instead of c so we don't get it confused with capacitance. Okay? So this is the result of the differential equation after I integrate it. Okay? These types of differential equations you can easily integrate in physics cases. You don't have to use integrating factors. And so what we want to do now is use the initial conditions to evaluate my constant here, but we want to write it in a slightly more suggestive form. So first of all, what are my initial conditions? Well, my initial conditions are that this equation is true at t equals 0, right when I flip my switch, okay? Right when I flip my switch and I start my stopwatch, my plates are fully charged. That is the condition we're going to use. More formally, we would say at t equals 0, q is equal to q naught, okay? So q here in my equation is going to be a function of time. And at t equals 0, it will equal its initial value, right? So to solve for q, what you want to do is exponentiate both sides. So we have this, and you can use the property E is equal, or E to the A plus B is equal to E to the A times E to the B, okay? When you have the same base with different exponents, it's the same thing as that base to one exponent multiplied by that base to the second exponent. And I can rewrite this as e to the negative t over rc times e to the k, right? But e to the k is just a number, right? It's still just a constant. So let's label this constant b, capital B. So q is going to equal b times e to the negative t over rc, okay? So already we can see something about what's going on here. We can already see that this is going to be an exponential decay. Why is this going to be an exponential decay? From a conceptual standpoint, when I flip the switch, some of the charge is going to flow off of my negative plates. But because there's a resistor here, the charge can't all flow at once. Only so much can. And so after one instant, some of the charge will be off of the plates. But the next instant, there's less charge on the plates, and so there's less charge to actually move off the next instant. And there's less charge to move off the next instant, and the next instant, and so on. And so the total amount of charge that can move off the plates decreases exponentially, okay? So now the task is to evaluate this integration constant, right? And we use our initial condition of at t0, q is equal to q naught. And so at q of 0, b times e to the 0 equals q naught. Okay, that's what our initial condition is telling us. Okay? And by that condition, what that tells us, e to the 0 is 1. And so this is just b times 1 equals q naught. So b is equal to q naught, which shouldn't come as a surprise. So what this tells us is that the charge on my plates, if I plug in 0 for t, once again, e to the 0 goes to 1. So at time 0, my plate is just fully charged. That's all that condition is telling me. And then as once I flip the switch, start my stopwatch, I can track then the charge to decay exponentially. But we don't typically actually track the charges. Okay, remember, electrons are really, 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 really tiny. I can't measure individual electrons in a circuit like this. What I'm going to do is I'm going to hook my meters in, I'm going to measure the voltage, and I'm going to measure the current. And I'm going to then infer that the voltage, or that the charge is diminishing. Okay, so how do those work? Well, first things first, let's write our result for the charge up here. So let's erase some of this. And we're going to have Q is equal to Q naught e to the negative t over RC. Okay? And let me write that a little bit bigger, actually. So hopefully that's a little bit more clear. How is the voltage across the capacitor going to behave? Okay? How is the voltage across the capacitor going to behave? And in fact, let's leave this condition up there. So the voltage from the capacitor you can find from this type of relationship, Q is equal to CV. Therefore, V is going to equal Q over C. Okay? But Q is the function Q naught e to the negative t over RC. And so this is going to be equal to Q naught over C times e to the negative t over RC. Okay? But from this relationship, if I divide both sides by C, Q naught over C is just equal to the initial voltage that the capacitor was charged to. So V is going to be equal to V naught, e to the negative t over RC. And because this equation must be true, the magnitude of the voltage, and I should say that this is the voltage across the capacitor, the voltage across the resistor has to stay the same in magnitude, right? We showed that earlier. And so because this equation is true, right, if I subtract VR from both sides, then these are just equal and opposite, and therefore their magnitudes are the same. Therefore, the voltage across the resistor will be the same. Okay? So far, everything is just exponentially decaying. And if I apply Ohm's law, remember Ohm's law is V equals IR, or I is equal to V over R. So if I divide both sides by the resistance, then this is going to be V naught over R e to the negative t over RC. But V naught over R is just the maximum current that the circuit could establish before the decay started. So V naught over R just represents the initial current in the system, right? So I is going to be equal to I naught times e to the negative t over RC. And so all of the quantities of interest, the charge across the capacitor, the voltage across the capacitor, the voltage across the resistor, and the current through the system, or the current through the circuit, all follow an exponentially decaying form here, okay? So that is what is happening here with the RC circuit when you have a charged capacitor connected to a resistor. Now, some notes and we'll do an example, all right? First things first, note that we have the factor e to the negative t over RC, okay? We have this factor e to the negative t over RC. Remember that those, the arguments of any exponential, trigonometric, or logarithmic functions must be unitless, hyperbolic functions as well. The units must, or the arguments must be unitless. So what that means is I have time over something. To be unitless, I need time over time for my seconds to cancel out. So what that means is ohms times farads must equal seconds. Okay, so RC is a unit of time. And further, we call this quantity RC the time constant. And we often label it with the Greek letter tau. Okay? So oftentimes what you will see is an equation like this, written like this. Okay? I naught times e to the negative t over tau. And tau is just the value of RC. Okay, so what is the time constant? The time constant, all right, if I let my experiment go, if I have meters in here, say measuring the voltage across the capacitor or the voltage across the resistor or an ammeter, pardon me, or an ammeter measuring the current, and I should find that the current would follow this form. Okay, and so if I let the current go, I flip my switch and I let my stopwatch go for one time constant such that t equals tau, then what I would find, since I is a function of time, if I let it go for one time constant, then I would have this, and this is just e to the negative 1, right? And what I would find is that e to the negative 1 is 0.367, if memory serves. 0.367. Okay? 0.368, I apologize. 0.368. And so what that means is, this is e to the negative 1. Let me erase these. So e to the negative 1 is approximately 0.368. Okay? And so what that means is I, at one time constant, would be 0.368 times the original current. Okay? So your current would have dropped from its original amount to 36.8% of its original amount. Or it would have lost, in other words, 63.2%. Okay? So if I plot my current as a function of time, right? And my current starts at some initial value, I naught, whatever I naught is, and I naught, remember, is going to be the initial voltage across the resistor, which the initial voltage across the resistor will be V naught, divided by the resistance. So I naught's just going to be V naught over R. And it will exponentially decay from this rule, and it would then approach 0. And so after one time constant, I will only have 0.368 of my original material left, somewhere around right in here. So that would be one time constant. Okay? And I'm losing 63.2%. Okay? I lose 63.2% in one time constant. So in one time constant, my current is going to have dropped by 63.2%. My voltage across both components will drop by 63.2%, and the charge on the plates will decrease by 63.2%. We theoretically, the exponential function never gets to 0. Practically, after 5 time constants, you can definitely call your capacitor discharged. After 5 time constants, you're over 99% discharged. 3 time constants gets you comfortably over 90%. It might even be closer to 95. I'd have to go back and look again. But 5 time constants is close to 99%. So after 5 time constants, whatever your time constant is, you can consider your capacitor effectively discharged. At that point, after 5 time constants, you should not measure any appreciable change in your current, and your current should be effectively 0. Your voltage across most components should be effectively 0. And as a result, your charge across your plates should be effectively 0. Okay? So now let's do a quick example. So if we do an example, and we'll give this nice numbers, okay? We will give this nice numbers. So suppose your capacitor is equal to 1 millifarad. Now that's a rather large capacitor, okay? And let's say our resistor is equal to 10 to the 4th ohms, or 10,000 ohms, okay? And let's suppose that the initial voltage across the capacitor, what it was charged to from the battery, is equal to 10 volts. Normally, I like to work in units of 12 volts, simply because that's more common. 10 volts is not really a very common value when you're working with batteries anyway. But for the sake of this example and make the numbers nice, we'll use 10 volts. So here are my questions, okay? Here are my questions. A, what is the total charge on the capacitor when it's initially charged? What is Q naught? B, what is the maximum current in the circuit? C, what is the time constant in the circuit? And D, at what time is my charge reduced by half? So at what time, or time equals what, when Q is equal to 1/2 Q naught, okay? What is the time when my charge has been reduced by 1/2? And because all of our equations follow the exact same form, what that means is when Q is equal to 1/2 of its original charge, the voltages will have dropped by half, the current will also have dropped by 1/2, okay? So let's answer these questions. So Q naught, remember Q naught is going to equal C times V naught. So this is 1 times 10 to the -3rd farads times 10 volts. So 1 times 10 to the -3rd times 10 is going to be 1 times 10 to the -2. And this is going to be coulombs since we're working with charge, right? So 1 times 10 to the -2 coulombs is the original charge on my plates. And my initial current in the system is just going to be the voltage that the capacitor was charged to divided by the resistance. So this is going to be 10 volts divided by 10 to the 4th ohms, or 10 divided by 10,000 is 1/1000th, or this is going to be 1 milliamp, okay? So my current is going to be 1 milliamp. What about my time constant? Well, my time constant is just equal to RC, so this is going to be 10,000 ohms times 1 times 10 to the -3rd farads. So this is going to turn into 10 seconds. Okay? So what that means is after 10 seconds, I will have dropped from 1 milliamp to 0.368 milliamps. After 2 seconds, I would then drop another 63.2% from that. After 30 seconds, it would drop another 63.2% from that, okay? Now, the real interesting thing happens right here. When Q has dropped by a half, at what time does that occur? Okay, so remember, since Q is a function of time, we write it like this. Okay, and so what I'm asking is, at what time is this side of my equation equal to 1/2 its initial value? Okay, so I'm going to write 1/2 Q naught on this side. And I'm wanting to solve for the time for when that occurs. So I want to solve this equation for the time. Okay, well, since I have Q naught on both sides, I can cancel those out. And I'm left with 1/2 is equal to e to the negative t over tau, right? And to undo the exponential, I take the logarithm of both sides. Okay? And at this point, if you're very clever, what you can do is note that the logarithm of 1/2 is the same thing as negative of the log of 2. Okay? And that allows you to cancel out the negative signs. And once you do that, now it's just a matter of multiplying by tau. And so t is equal to the time constant multiplied by the logarithm of 2, or the natural log of 2. Okay? So this is what's often known as the half-life. This is the amount of time it takes for the system to drop its values by a factor of 2, or it dropped from its original value to half of its original value. Okay? So since we know what RC is, 10 seconds, if you take the natural log of 2, you should find it's like 0.693 or something like that, if memory serves. Okay, and again, the natural log doesn't have a unit in its argument, so this is a unitless number multiplied by 10 seconds. So what this is telling you is after 6.93 seconds, our values will have dropped by 1/2. And if you think about it, that should make some sense. If it takes 10 seconds for our system to drop by 63.2%, then it should take a little bit less time than that to drop by 1/2. And sure enough, 6.93 seconds fits that bill. Okay? So that is the RC circuit when you are discharging your capacitor. In the next video, we'll talk about when you're charging your capacitor, and upcoming is magnetism. So stay tuned. We'll see you then.